Okay, so the first step to answer this question and do this approximate full space-time discretization is to first, when we discretize this problem in space. So that is the first thing that we do. So let me just write it down. Step 1. Discretize in space. So let me start by discretizing this equation in space. So assume this is your x direction, and this is one-dimensional equation, and you might have higher dimensions, right, depending on the problem that you are solving. So this is x direction, say, and here we are solving from 0 to L based on the problem, right? Here it is. And say here I have, let me say here L. This is, say, my first point, and then I'm going to discretize it. So this is going to be the second point. This is going to be third point. This is going to be fourth point, and this goes on and on until there. Okay. So this is, let me just yeah, x2, this is x3, and then the last one is going to be xn. Okay, so this is how I name and discretize x. Okay, space. So now I have this equation, and I want to write and solve this equation along these nodes, along these grids, these cells, whatever you want to call them. So partial u over partial t plus v, partial u over partial x, minus d, partial square u over partial x squared, plus kappa u, and then I'm going to just bring that f to the left hand side, minus f. This is my equation evaluated at xi, at any xi. This should equal to 0. Okay, and this is valid for everything except the I want to solve this everything except the boundary conditions, right? Because the boundary conditions are given here, so I don't really need them. So the one here is going to be from I equals to 2. So this one is clearly given. This one, I'm going to find this out later, but we need a relationship for that one too. So this is, I'm going to set it, instead of I equal to 1, which is from here, the left boundary, equal to 2 to n. Okay, so it's going to be 2, 3. This I can be any of them. And the other thing I'm going to assume is this delta x. I'm going to assume delta x is constant, so I don't want to deal with kind of variable xi's, variable distances that can make my numerical scheme more complex. But in fact, if you're you want to develop a very general method, you should consider also variable delta x depending on your problem. So these are going to give me n minus 1 equations, right? Because I have it from 2, 3, 4, 5 to n. And then the other equation that I have is one equation that is left. Is u1 equals to the given number here, u left. Okay. Okay. So this is the discretization, and now I want to do, after this, I want to do spatial finite difference approximation to approximate the all these terms in this equation based on the nodal value, based on their nodal value. So let's see how does this look like. Okay. So I'm gonna have spatial finite difference approximations so I'm gonna just approximate all the terms here that I have, okay, like all of them, and let's see what they will be. So the first term I'm gonna approximate is v partial u over partial x. I'm gonna approximate it in two ways. You can use all the methods that you have learned so far, from center difference, forward difference, backward difference, all of them, okay? So the one I'm gonna use is center difference method, ui plus 1 at t minus ui minus 1, and the difference is now we also have time, right? So we have to be careful about that, and we will delve into that later in the second step. The first step is just discretization in space over 2 delta x, and then the second case I'm going to use a variable weighted method. So ui alpha ui minus ui minus 1 over delta x plus 1 minus alpha ui plus 1 minus ui minus 1 over 2 delta x. So I'm going to call this case A, because you can have different cases, right, based on the approximation that you choose. So this is case A, and I'm going to call this one case B. Okay, so this is the first term I approximate. The second term is the diffusion term. So this partial square u over partial x square is approximated as second order center difference scheme ui plus 1 minus 2 ui plus ui minus 1 over delta x square. So this is the approximation for this one. Then I want to approximate ku here. So ku, so this is one thing I forgot. This is represented at point I, or approximated at point I. So the same thing here, ku approximated at I, node I. I can do it, let me write it down here. I can do this two ways. So ku at I can either, so I can approximate it in two ways. The simpler thing is that you might think, okay, it's just kui, right? But I can also do something else, and that is approximated based on the value at that node and also its surrounding nodes. So k mu minus 1 ui minus 1 plus mu 0 ui plus mu plus 1 ui plus 1. Okay, so I'm going to call this one case C. I'm going to call this one case D. And why I do this? The reason I do this is sometimes you can do this to remove truncation errors, or in other words, improve your approximation. So for example, an order delta x square approximation can be written as this: 1 minus mu times ui minus 1 plus 2 mu ui plus 1 minus mu ui plus 1 over 2. And this is going to be an order delta x square scheme. Okay, so this is sometimes we do it to improve the approximation. And finally, I have partial u, partial t, again evaluated at I. I can write it again in two ways. One is I just write it as dui over dui as a function of t, which is a function of t. So dui over dt. And this one a little bit, write it again. So dui dt. And the second one, I'm going to use something like this one. So I'm going to say 1 minus beta over 2 times dui minus 1 dt plus beta dui over dt plus 1 minus beta over 2 dui plus 1 over dt. And this one I'm going to call it case E. And this one I'm going to call it case F. And you can choose any of this combination. So here, what I've proposed, you can choose 8 combinations, 2 times 2 times 2, right? So I'm gonna, now that I have all the terms of this equation in terms of their nodal values approximated, finite difference approximation, I'm gonna choose the simplest one. So let's choose the simplest cases of A, C, right, C, and E. This is the simplest case, okay? So let's write the equations in terms of that. So E is this one. So I'm going to write it as DUI over dt plus C, the second term, which is VDU over dx, is B, which, is A. So is this one. So I'm going to have V UI plus 1 minus UI minus 1 over 2 delta x minus D, and then the next one is E. So the next one is C, sorry, which is going to be kappa U. And this one is, I only wrote one approximation, so I'm going to just use that. UI plus 1 minus 2 UI plus UI minus 1 over delta x squared plus kappa UI equals to F xi and t. Okay, so this is the discretized equation in space. Okay, we have not touched the time yet, and we are going to do it later. But before doing that, I want to go further and simplify these equations and write these equations, all these equations, as a matrix. A matrix where you can easily solve it in computer or other programming frameworks. So let's see. So my general equation, I can write it as this. So I have DUI over DT plus, I'm going to just factor everything from UI minus 1, so it's going to be minus V over 2 delta x plus D over delta x squared or times UI minus 1 plus 2D over delta x squared plus kappa times UI, so I factored UI, and the last term is going to be V over 2 delta x minus D over delta x squared UI plus 1 equals to Fi. Okay, so this is going to be my general equation. And I convert this to a simpler form. So I'm going to say it's like DUI over DT. And instead of this, I'm going to just use let me do it with this. So instead of this, I'm going to just use A1, AI. So it's going to be AI UI minus 1 plus, instead of the second one, I'm going to use BI. So BI UI so BI UI, and the last one is going to be CI UI plus 1 equals to Fi. So it's going to be this BI and it's going to be CI, where I equals to 2, 3, up to n. Okay, so this is a simplified form of equation. You can do this for all types of kind of approximations and PDEs that you are trying to solve. Okay, so I have now the general equation for I equals 2, 3 to n. And then the next step before creating forming a matrix and putting this into a matrix form, what I want to do is apply boundary conditions. So I'm going to applying boundary conditions. Okay. So the first boundary condition is U1 is U left. And the second one is this one. So the first one is simple. So let's just do that. And for that, because in the equation I equals to 2, if I equals to 2, I'm going to have U1 here. So I'm going to use it there. So equation I equals to 2, that is where it appears. So I have du2 over dt plus a2 u1 plus b2 u2 plus c2 u3 equals to f2. And we know from here that u1 equals to u left. So I just write it down there. So U1 is U left. So I will just move the whole thing onto the right-hand side of this equation. Okay. So what I'm going to have for equation I equals to 2, it is du2 over dt plus b2 u2 plus c2 u3 equals to f2 minus a2 u left. So this is the first equation that I have. Okay. And then the next one is going to be for the right boundary condition. So I'm going to apply it to the last equation. So equation, and let's see, equation I equals to n, right? Because that is where I'm going to have, I can use the right boundary condition here. The right boundary condition is simply here, right? Okay. So here, for the right boundary condition, we're going to use a trick. For the right boundary condition, we don't have this Dirichlet kind of boundary condition. We have this boundary condition, okay? Gradient boundary condition. So what I'm going to do is I'm going to write, I first write the equation. So the equation I have here is going to be du n over dt plus an un minus 1 plus bn un plus cn un plus 1 equals to fn. Okay. So in this equation, we don't have un plus 1, right? We don't know what it is. It is out of our domain. The last term here that we had was xn, right? So what I'm going to do here, we're going to use a trick. We don't have this, so we use domain extension. We use domain extension. So I just write it down here. We do domain or virtual domain extension. It is not real, but we just do that, and then we write that in terms of our available variables. Okay, so let's see what it is. So what I'm going to do is say this is our domain. Let me put it here. So we have it here, we have 3 points here. This is, say, xn. This is xn minus 1. And this is the extra point that I'm going to add, which is xn plus 1. Okay? This is kind of imaginary node. Sometimes they call it even ghost nodes, right? So it depends on the literature. They might call it even ghost nodes. So what I'm going to do after this, I'm going to use the boundary conditions to relate this, the value of u at this node, to un and un minus 1. So let's see how is that. So use boundary condition to relate un plus 1 to un and un minus 1. Okay. So I have partial u or partial x evaluated at L equals to 0. So this is the boundary condition I have. So I can just write partial u over partial x at xn can be approximated as un plus 1 minus un minus 1 over 2 delta x, right? And this is the delta x I have. I assume they are constant. And this is essentially 0 based on the boundary condition that I have here. So this tells me, this boundary condition indicates that un plus 1 should equal to un minus 1. And this is an important finding. So we are going to put this into the FDA, the finite difference approximation, at xn, which is here. So the equation that we have is going to be dun over dt plus an un minus 1 plus bn un plus, instead of cn un plus 1, I'm going to write cn un minus 1 equals to fn. And this can be reduced to un over dt plus, so I'm going to factor un minus 1, so I need to change the coefficient of un minus 1, which is going to be an plus cn times un minus 1 plus bn un equals to fn. So this is going to be my equation. The second equation, which is the equation I equals to n. So I have now two equations. And so the final one is going to be equations I equals to 3, 4, 2, n minus 1. And those are simple. Those are the ones that we found here, the general equation. Because they are not, we don't care about the boundary conditions, or we are not worried about the boundary conditions there because of the way we have approximated it, okay? Because we only go up to ui plus 1 and ui minus 1. So if we were going further in points, we had to apply the boundary conditions further. But because we don't go, so for these intermediate nodes, the equations is going to be just the general equation that we have, which is dui over dt plus ai ui minus 1 plus bi ui plus ci ui plus 1 equals to fi. So these are n equations that I gotta solve to be able to solve this system, okay? So now I have those n minus 1 equations, these n minus 1 equations, and the next step would be to put them into a matrix form so we can represent it in a computer code. And after that, we are going to do the time stepping, the time marching method, okay? How to apply time marching here, especially for this variable here, right? We don't know what it is and how to do that. So I will do that in the next lecture. And after that, this example will be done. Thank you very much, everyone.